Well, in our last video on undamped systems, we're going to show a theorem and then one more example. And just as something to look forward to, when you have an equation like this, like we've been dealing with, this is the undamped. There's no dash pot. There's no, it's not in liquid. In the damped systems, we're going to pull these apart and we're going to have not just a second derivative and an x, we're going to have the first derivative. So velocity is going to come into play. Okay, well, let's get this last video on the undamped systems done. Here's a theorem. It's pretty good. It basically tells you what your C1 and C2 parameters are. So a mass m that stretches a spring a distance s, like we always define it, satisfies this initial value problem, which is exactly what we've been solving. X naught is the initial x position. X prime of 0 is v0, the initial velocity. Here's the solution. That's your C1 and that's your C2. And then omega, of course, is used in this equation, so we're just redefining it. It might look, well, this looks identical to what it is, but here's another way of stating what omega is. And it shouldn't be a surprise, because if you took the radicals away, if you squared both sides and you cross multiplied, you get mg equals ks. So these two are equal to each other. So the first term, the cosine term, is dependent upon the position, and the second term is dependent upon the initial, I should have said initial position. The second term is dependent upon the initial velocity. So in this example, we won't have to solve for C1 and C2, we'll just use that theorem. Okay, a 2-pound mass stretches the spring from its natural length, it stretches it 6 inches. At time t equals 0, the mass is released from 8 inches below equilibrium with an upward velocity of 4/3 feet per second. Find the equation of motion. All right, well, let's write down everything we know. What's m? M is 2 divided by 32, right? So 1 over 16. And I don't think I'd mentioned this, but the units, we're going from 2 pounds to what? 1 over 16, we call that slugs, a slug. So when you divide the pounds by the gravity component, it's called a slug. So m is 1/16 slugs. What is the initial position? At time t equals 0, the mass is released from 8 inches below equilibrium. Below means positive. 8 inches in feet would be 8 over 12, or 2/3. The velocity is not 0 this time because they're applying some upward velocity of 4/3 feet per second. So upward, that means the velocity is negative. If it were going downward, it's positive. Upward is negative. So negative 4/3. So I could have said released from 8 inches below equilibrium with velocity negative 4/3 feet per second, instead of saying upward 4/3. All right, force equals K times S. This is going to help us get K. So what do we know? We know that S is what? S is 1/2. And the force, this is just the initial mass times gravity. It's the pounds, it's the 2 pounds. 2 is equal to K times 1/2. So K is going to be a 4 for us, 4 pounds per foot. So let me put K equals 4 pounds per foot. Okay, omega is defined to be that, which would be 4 over m, 4 over 1/16 under a radical. Radical 64, and that makes it an 8. So W squared is 64, W squared, omega squared. So our differential equation, I think, is identical to the last, where we have x plus 64, x prime prime or x double dot, second derivative with respect to time. So that's our equation, and it'll be the solution, or the general solution will be exactly the same as it was last time. But let's just go ahead and use the theorem. By the previous theorem, x of t is equal to, C1 was the initial position. The initial position x naught is 2/3 cos omega t plus, I forgot what that one is, it's velocity, initial velocity over, over omega. So initial velocity, negative 4/3, initial velocity over omega is negative 4/3 over, and omega was 8. So that's going to be equal to negative 4 over 24. I got negative 1/6, and that's correct. So that's going to be a minus 1/6 sine 8t. So that was pretty simple using the theorem. So all we needed was omega and those two components. So we had to go through some of this to get omega. And that's it. So the next video series will be on damped spring mass systems.